Today's video is the third video in our series on mathematical induction, and today we're going to look at how mathematical induction has an interesting application to a problem on the 2005 Putnam. It's the first problem on the exam. And the problem asks to prove that any positive integer n can be written as a sum of the form 2 to the r, 3 to the s, so a sum of numbers that are themselves a power of 2 times a power of 3, but with the added condition that no summand divides another. So as an example, if we took the number 23, one way that we could do this is write it as 9 plus 8 plus 6, and we notice that each of these numbers here are of the form that we're asked, and no summand divides another. Now, one of the things on the Putnam is you're not told how to actually solve a problem, and this problem at first might not seem like a problem that's amenable to induction methods. But I want to look at a classic problem where we get rid of the power of 3 and ask for a number to be written as sums of powers of 2 to get an insight on why induction might be a good method to go. So the problem I want to look at is essentially why every positive integer has a binary expansion. Another way to word this is that every positive integer can be written as a sum of distinct powers of 2. Right, so for example, 7 can be written as 4 plus 2 plus 1. And that gives us the binary expansion 1, 1, 1 when we write 7 in binary. This corresponds to the 4 here, to the 2, and here to the 1. Okay, for our base case, we have n equals 1. In that case, we can write n as the power 2 to the 0, and so we're good to go. Now what about our inductive step? Well, we'll assume that every single positive integer less than our given positive integer n has a binary expansion, meaning it can be written as a sum of powers of 2 where all the powers of 2 are distinct. So what should we do with the actual number n itself? What we can do is take out as much of a power of 2 as possible. So we'll let 2 to the r be the highest power of 2 less than or equal to n. If that happens to be n itself, that's possible, n could be a power of 2, then we're happy we've written n as a sum of powers of 2. Okay, but if n is not equal to 2 to the r, then what we can do is consider the number m, which is n minus 2 to the r, and this is strictly less than n. Now what we know about m is m itself can be written in this form as a sum of powers of 2 because m is smaller than n, and we assumed inductively that the number smaller than n can be written in that form. Okay, so what we have then is that m itself is a sum of powers of 2. I'll write them as 2 to the alpha. And so n is 2 to the r plus the sum of these numbers 2 to the alpha. Now, instead of writing this as an arbitrary 2 to the alpha type thing, what we want to do is be careful because we need to know that all of these summands are actually distinct, and we don't know that yet. So let's be careful and write m as an explicit sum of powers of 2 and analyze the situation. So let's say m is 2 to the a1 plus 2 to the a2, etc. up to 2 to the a sub k. Then n is 2 to the r plus all of the stuff that we had before. Okay, we know that this is a sum consisting of distinct powers of 2 by induction. So the question is, how do we know that this entire list is a sum of distinct powers of 2? Well, let's say it wasn't. Then one of these here would be 2 to the r. Okay, but if that's the case, then adding this 2 to the r right over here, we get that n is greater than or equal to 2 to the r plus 1, and that actually contradicts our choice of 2 to the r being the highest power of 2 that's less than or equal to n, because now we have another power, 2 to the r plus 1, that's still less than or equal to n. Okay, so that means that all of these powers are actually distinct, and so inductively we have that any number has a binary expansion. So let's see how we can use this to motivate a solution to the problem that we had on the Putnam exam. Okay, so let's see how we can use binary expansion as a motivation for solving this problem from the 2005 Putnam. So again, the problem is, for any positive integer, prove you can write it as a sum of terms like this, where no summand divides any other. So from inspiration with binary expansion, we'll prove this by induction on n. Now the base case, when n is 1, we can write it as 2 to the 0, 3 to the 0. And so that's a quick base case there. We have one summand and no summand divides another because we only have one summand. So let's move on to the inductive step and assume that the statement is true for all positive integers less than this n right over here. Now what can we do? Well, first of all, we're going to do some pre-processing. If n is even, n over 2 can be written as a sum of the form that we're interested in. So say something like 2 to the a1, 3 to the b1, plus all the way to 2 to the ak, 3 to the bk, where no summand divides another. Well, if none of these things divide another, then we can multiply by 2, and that would increase all of the exponents on the 2 powers by 1. And subsequently, none of the subsequent summands are going to divide each other either. So in the case that n is even, the induction actually works out a little bit more straightforward than in general, and so we're happy. So what we're going to do is assume then that n is odd and see what happens. So what should we do if n is odd? Well, we can employ the same idea that we did in the binary expansion situation. We can let 3 to the k be the highest power of 3 that's less than or equal to n. Alright, so then we'll consider the number n minus 3 to the k. Now since n is odd, n minus 3 to the k is also odd, so we'll go ahead and divide that by 2. Now this is a number that's strictly less than n, so inductively we can write this as a sum of powers of 2 and 3 multiplied, where no summand divides any other. So we'll have something like this up to 2a to the r, 3b to the r. Okay, so now if we rearrange this, we get n is, we're going to have a 3 to the k, and then we're going to have summands that look like 2a1 plus 1, 3 to the b1, all the way up to 2ar plus 1, 3 to the br. Now if we look at this situation, we see that because none of these summands divided each other, none of these divide each other because we just multiplied every single one of them by 2 like we did in the even case. But now we only have one more summand for n, and it's this power of 3. And since this is a power of 3, it's odd, none of these divide each other at all, right? This can't divide any of these, because if this did divide one of these, then we would have, say, 2a1 plus 1 times 3b1, where this b1 is at least k. If that was the case, then this number here is at least 2 times 3 to the k, which would mean that n itself would be at least 3 to the k plus 2 times 3 to the k, which is 3 to the k plus 1. And that's a contradiction from the fact that 3 to the k is the highest power of 3 that's less than or equal to n. So there's no way 3 to the k divides any of these. And then similarly, we see that none of these divides 3 to the k because all of these are actually even numbers. So I think this is a really cool, interesting problem, especially thinking about it inductively, because at first it doesn't seem exactly like it might be a problem that is amenable to induction, but inheriting the idea of binary expansion allows us to get a meaningful inductive proof.